Hello everyone, welcome to this video. In this video we'll be looking at examples of two-step subgroup test. So before that, let's see what is the procedure for two-step subgroup test. So here we first of all use the assumption that both the elements A and the element B, they have the property P, and we will prove that first of all that AB also follow the property P, and then A inverse also follow the property P. So this is our aim here, right? So that is why this is known as a two-step subgroup test, because here we have two steps involved, right? So let's move on to our first example. So we assume that G is an abelian group, right? So we will prove that H, which is defined like this, it contains all the elements from the group G such that the order of that element is finite. Now notice that here mod x, that represents the order of the element and not the order of the group. So we are saying order of the element is finite. All the elements of such kind, they are present in H, and this H would then form a subgroup of the group G, right? So for that we start with the same thing. That means we'll first show that identity is present in H such that H is non-empty in nature. If this is non-empty in nature, so we say e to the power 1, that is E only, right? So that means you can say that the order of the element E is exactly equal to 1. So that means this order is finite, and if the order is finite, so that means the element E is definitely would be there in the set H. So that means this set H, that is non-empty in nature. So we next assume that the elements A and B, they are present in the set H. So here in this case we will prove that the elements, the product AB is present in H, and we will prove that A inverse 1 is also present in H. So this is what we will be proving here. So for that we assume that the order of A is exactly equal to M and the order of the element B is equal to N. Why we are able to do so? Because both A and B, they are present in H, and so that means both A and B would have finite order. So let us call that the order of first one is M and the order of second one is N. So now let's consider this AB to the power mn by ourselves. So it would be equal to A to the power mn and B to the power mn. So you could write this to be like this: A to the power m to the power n, and you can write this to be like this: B to the power n to the power m, right? Why we have written it like this? Because A to the power m is nothing but equal to, it is equal to m, because the order of A is equal to m. So that means A to the power m is equal to E, and the order of B is n. So that means B to the power n is equal to E. So substituting these values here, we have E to the power n, and in place of B to the power n, substituting E here, so we have E to the power m. E to the power n is again E, E to the power m is also E, and E multiplied with E is E only, that is identity. So therefore AB has finite order. So here we cannot say, because we obtain that AB raised to power mn is equal to E, right? For some finite number we are able to get this identity, but it may be possible that this mn is not the smallest integer of such kind such that we obtain identity. So we are not sure that this mn, whether this is the order here or not, but we are sure that because we obtain it for identity, so that means we obtain identity for this number mn, which is finite. So therefore any the order would be any number which is either equal to this mn or it is lesser than mn. So in that case also it is going to be finite. So we say AB, the element AB now has finite order, and therefore it is a member of the given set H, right? The next thing we can see here, we wanted to prove that A inverse is present in H. So for that we wanted to prove that A inverse has a finite order. So for that we assume that A inverse m, A inverse to the power m, it is equal to A to the power m raised to power minus 1. And what is A to the power m? It is equal to E, because the order of A is equal to m, right? So A to the power m is equal to E. So using this thing here, we have E to the power minus 1, and E to the power minus 1 is E only, the identity of the group. So therefore, because we obtain A inverse raised to power m, that is equal to identity, and m is some finite number. So that means the order would surely be either equal to m or it is less than equal to m. Less than m. Why it is so? Because order is that smallest positive integer for which we obtain identity. So we obtain an identity here for m, so the number could either be m or it could be smaller than m. So we may not call m to be surely to be the order here, because we are not sure it is that smallest integer. So but we are sure that the order is finite by seeing at this thing. So if A inverse has finite order, so that means this A inverse would be a member of the given set H. So that means by two-step subgroup test, H is a subgroup of the group G. And this is what we wanted to prove here in this example. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.